So again, the frictional force is proportional to the normal force, because if you push down and try and slide your hand across the table, you'll feel it's much more difficult. Remember that it is a reaction force. Remember we talked about action and reaction pairs? So every time you take a step, you push forward. The action force is you pushing. The reaction is friction pushing you forward. That's how you step every day. It's friction between your shoe and the ground that's actually providing that forward force to help you walk across the room. Okay, it's friction that's helping you. Another type of friction that people don't realize usually that helps you is your tires. That's how you move forward. The rubber, or the friction between the rubber and the ground, is what propels the car forward, as opposed to stopping you. Most people think friction is always a resistive force, that it's going to slow down your motion. Well, if you're jogging or you're going for a run and the wind is pushing back against you, that friction is slowing you down. Or if you're driving your car, the air resistance is slowing you down. But the friction between the tire and the ground is actually helping you move forward. So there are many different types of friction. In basic physics, or in this physics course, what we're going to really study is friction that slows down motion. Okay, friction that slows down motion. Now, if you go on to take dynamics, or if you study engineering, you're going to learn about rolling friction, the friction between the tire and the ground that actually propels you forward. So again, what we're going to do is identify the types of frictions, but really what we're going to study mathematically is friction that acts as a resistive force. Now, the one thing you want to notice is no matter how smooth two objects are, there's always friction. There is always friction. But you can reduce that friction by certain methods. What's one way of reducing friction? What's one way? Water. Okay? So some sort of a fluid on the surface. So if you're running, say you have a piece of wood, and a piece of wood is running over a conveyor belt, if that conveyor belt has some sort of a fluid on it, it will technically, or will usually, lower the value of the friction constant. And we'll talk about how that constant works in a minute. But there are ways to lower friction. What about, have you heard of Teflon before? Anybody know what Teflon is? Teflon? Relax, stop, guys. So, if he knows, he can raise his own hand. Relax. So, Teflon reduces friction dramatically. Now, on the bottom of a sofa, if you want to move a sofa in your house, you buy these Teflon squares, and one side of it is a sticky side. You stick it to the four corners of the four legs of the couch, and you can slide it across the floor very easily. Teflon it's a very, very low friction material, and it slides easily on wood, on metal, on anything. Now, another example of Teflon are pans. If you ever cook on a pan that's made of Teflon, you'll notice that it cleans very easily.
Non-stick?
Yeah, exactly, Jeff. Very good. A non-stick there. Those non-stick ones are the Teflon.
If you scratch it, it's like...
Yeah, if you use a non-stick too much and you use a metal spatula, you can actually rip off the Teflon, which is something that could harm you because it can go into your food. Okay, that's why they tell you to use a plastic spatula on those pans because it comes off so easily. And when you clean it with a sponge, you can use the soft side of the sponge because it cleans so easily. Teflon is low friction, low friction. Now, there are types of friction, and this is logical because you're going to notice if you want to move this desk across the room, to get it moving, it's pretty tough, just to get it started. So if I wanted to move this across the room, just to get it started, I have to put a lot of force. But once you get it started, what happens? What do you notice? It's pretty easier. You feel like you pick up momentum in a sense, right? You get this started by pushing it, so I've got to really push to get it started. But once you get it going, it's going to slide very easily. But again, to get it started is tough, but once you start moving, it's pretty easy to move. Now, the reason for that is pretty tough to think about, but it makes sense. Between the molecules, between the surfaces, there's an electrostatic force that causes the surfaces to want to cling to one another. Now, once that force is broken, once those molecules are no longer in contact, and now it's sliding, the electrostatic force reduces. So what we call this in physics is the difference between static and kinetic friction. What does the term static mean to you? Static. Where have you heard it before? Paul. Still, very good. Or not moving. So the force of friction that you need to overcome to start this desk, to get it moving, is called the static friction. friction force. Static friction force. As opposed to the frictional force that you will feel once it starts to move, which is called the kinetic. And kinetic means moving. Kinetic or kinematics we've been talking about are particles that are moving. So kinetic friction is the force you overcome once you get it to start moving. Let me see what I wrote here. So again, if you want to define static, just to define static friction, the resistive force that opposes the relative motion of two surfaces that are at rest. That are at rest. So whenever something is not moving and you're trying to get it started moving, it's going to be overcoming the static friction force. If it's already moving, if it's gliding across the room, you are then combating the kinetic friction force. Again, these are non-moving. And the key here is this, by the way. Please underline this at the end. With respect to one another. And I'll explain what I mean. Draw yourself a little truck, a flatbed. Now, in the flatbed, you've got a box. You've got a box in the trunk of the flatbed truck. On top of that, you've got another box. Okay? So you've got a box on top of a box. If the box, or the truck starts moving forward, right? If the truck starts moving forward, the top box might slide off of the bottom box, right? It might slide off of it because it's not being tied down. Obviously, if you were driving, you would put like a, some sort of a elastic cord or a rubber cord around it, or a bungee cord to hold it. Now, imagine you didn't have that though. The thing is this, even if the car is moving, between these two boxes is static friction. Because they are not moving with respect to one another at first. Again, I've got an object on top of an object. Okay, these two objects stacked together. Even though my body is moving and my arm is moving, the frictional force between these objects is static because they're still with regards to one another. Again, they are stationary. They're not moving. They're not sliding across each other. There is static friction. Now watch what happens. If I move my hand too fast, what's going to happen?
No way.
What force do we have then? Because this is moving, it's sliding, it's kinetic friction force. Again, it's static right now, but once this bottom object moves fast enough, it's going to be the kinetic friction force between these two, which is very low, as you can see. As opposed to having two pieces of wood on top of each other, and you try to do that, it's not going to work as easy, right? So, static means not moving. The two objects or the two surfaces are not moving. Again, it's very important that you notice that because we're going to have problems where you have a truck moving with two objects on top of it. If they're not moving with respect to each other, it's static friction. If they're sliding around, then it's kinetic friction. Okay, then it's kinetic.
What if one is moving and the other is...
It's kinetic. So they both have to be at rest with respect to each other. The bottom one could be stationary, and the top one could be sliding. That's kinetic, because they're moving with respect to each other. Okay? So kinetic is almost the exact same definition, really, except the motion of the two surfaces are moving past one another. Okay, the relative motion of them moving past one another. So again, it's all about the surfaces. It has nothing to do with the object and what it's sitting on top of. It's about the surface contacts. If those surfaces are gliding across one another, you have friction. And you all know that in the winter you do this. You do this to create friction, to create Q, which is called heat. Q, heat between your hands. You do that so your hands warm up. It's friction. Okay? Questions? Any questions? So static is stationary, kinetic is moving. Now, a minute ago we said that the force of friction was proportional to the normal force. It needs to have some sort of constant though. Like earlier this section, we said that the net force was proportional to the acceleration. And we said, well, what was the proportional bond? We said F equals ma. M was my constant, right? Again, in the beginning of chapter 4, we said that the net force acting on an object is proportional to its acceleration. By what value it turned out to be m? Well, in this case, we call this mu, which is like our micro symbol from earlier this year, when we talked about 10 to the negative 6, or micrometers, or microseconds, or, I don't know, what else, micronewtons. That micro symbol represented 10 to the negative 6. It's now representing our constant, and that is based on the two materials. So if you want to write this is pronounced mu, mu. And it can be mu-s, meaning static friction, and it can be mu-k, meaning kinetic friction. So you can have static and you can have kinetic. Now, mu is a surface or material property.
Can we turn on the air?
Sure. Want to hit the air and shut the window?
I don't even have to.
A little more. So mu, just hit the window, please. Thank you. I don't want to waste the picture. Mu is the surface or material property. Now, think logically for a second. If there's more friction because the surfaces are rough. So if you have wood and you have rusty metal, and you try to rub rusty metal across a wooden surface, you're going to feel a lot of resistance, as opposed to this plastic bottle here gliding easily across this desk. I mean, look at the difference. This is very easy to move. But if I took a piece of rusty metal and tried to do that across a rough wood surface, it would be very difficult, right? So the frictional coefficient is much higher for the wood and the rusty metal. So let's write this. As mu increases, the force of friction increases. And that is very evident if you look at the formula. Take a look here. If this number were 5, you would do 5 times the normal force to get friction. But the minute this goes to 10, now your friction force has doubled. If this were 20, then the friction force has quadrupled, and so forth and so on. So as mu goes up, the friction force goes up. Again, mu is our constant that describes the interaction between the surfaces. It's a coefficient of friction. Okay, a friction coefficient, or a coefficient of friction. And again, mu is just a descriptor. It tells us about our two surfaces and how they interact with one another. So again, the higher the mu, the more rough the surfaces are. The lower the mu, the smoother the surfaces are. So Teflon would have a very low mu value. Very low. Whereas something like wood, or rusty metal, or, I don't know, rubber. So for example, take an eraser, and you go to erase something off your paper. Doesn't the eraser fall to pieces on your paper? Because there's a lot of friction there, and the frictional force is overcoming the tensile strength of the rubber, which causes it to break into little pieces and rub off on the paper. So rubber has a high mu value. Now, in your textbook, in section 4.4, and I'll tell you what page so you can write it down. There are some that are almost frictionless, yeah. Remember that video I put a video on news, or I can show you in class if I forget, where there was a magnetic object that was rotating around a circular track and it was hovering above the track. It was called quantum mechanics. That was an almost frictionless situation. It was, if you look on the news, go home and look on the Moodle on the news, you'll see I put something with, it's quantum friction it was called, where it's an object that's moving with some electrostatic force around a track. That's an almost frictionless condition. You know what else is almost frictionless? Anybody ski or snowboard?
Yes, I ski.
You ski? Okay, I ski also. If you ski or snowboard, the surfaces between that snowboard or ski and the snow is almost frictionless. It really is. Until you turn and go to stop. We all know when you stop on a snowboard, you lift your front so that it drags along the ground. If you stop with a ski, you turn to the side and you angle it so that it grinds. so that it actually digs into the snow to stop you. If you don't do that, what's going to happen?
You go,
You're going to keep going, right? You're not going to stop. Unless you know how to stop, it ain't going to work. You're going to go right off the cliff or smoke. So on page, write this down please, page 144. Page 144, there's a table with all of these values. So it says, hold on one second. It says, for example, steel on steel, rubber on concrete, rubber on wet concrete, glass on glass, Teflon on Teflon, which is the smallest of all of them. Okay? So you're going to see this table. When you work on your homework problems, you might want to reference this table to help you. Is that clear? On a test, you'd be given the value in a table, or I'll just give you the value in the problem. Okay, but know how to use this table. Jeff?
We don't consider like doing something to help.
Yeah. What do you mean? Oh,
Are they kind of, are they just like?
yes, they are. Absolutely. So, Jeff's question is really good. If you want to slide an object across the floor, and it's really heavy, you put it on a dolly, right? And then you roll it across the floor. It makes it a lot easier. Because wheels reduce the overall friction between the surfaces. You know why? Because there's no abrasion. There's no running across of a surface. Like, if I do this, and I slide this like this, I can feel the abrasion, or the forces between them. Whereas this, it's a rolling technique. So it just continues to roll. That's not working well because of the material here. But if you roll something, you're going to see it rolls much easier than it slides. When you slide, you can feel the friction. When you roll it, there's almost no friction there. You can barely feel it. Now, remember, rolling friction can also help you in the case of a tire because it propels your car forward. And that's why you put it on the tire, because it pushes you forward in that case. Because what? Exactly. Also, people, when you hit your brakes, why do you have ABS in your car? Why do you have an anti-lock brake system in your car?
The brakes don't like slam on.
Yeah, because the tires can lock up, then it would just slide on one piece of the tire, which would cause it to burn the rubber. You want the car to then pulsate, and that's why you'll feel, anybody ever driven before, you'll feel the brake bump you like this if you hit it too hard. That's the anti-lock brake system kicking in. It's causing the tires not to lock up. It'll cause them to brake, rotate, so that you're braking on different parts of the tire, and you don't just slide across the floor. And if you have a wet surface, and you don't have anti-lock brake system, your car is going to hydroplane, which means, anybody know what hydroplaning actually means?
You get too much water. That's what you're running the, I mean, together. I know that you just are not supposed to go.
I know.
Okay, it has to do with puddles of water. You're right about that.
It's basically like what you were talking about before with water and friction. Like when the rubber goes on the wheels, like it can lose control and it'll just,
Okay, the idea is there's more to it. There's a little more.
If you brake too hard, then the wheels would slide and you wouldn't stop.
Still more.
Thanks for
You're on the right track.
Yeah.
Between the, like a layer of water forms between the ground and the wheel, and you have almost no friction.
Okay, there's one more thing or you're all forgetting about it. Hydroplaning is not really about water, believe it or not. You know that? The word hydro means water, so you think hydroplaning is water. It's not, Russ. In the ground, there are oil pockets that are automatically like just going to sit there and sit in little pockets. So, for example, in asphalt, there's little bits of oil in those little holes that you see in the asphalt. The minute it starts to rain, the density of water is greater than that of oil. It actually seeps under the oil, causing the oil to rise to the surface. And you see that like slick, almost like it looks like a rainbow on the ground. You see like a rainbow? It's the oil slick surface. And when you hydroplane, hydroplaning traditionally occurs within about 5 minutes of the rain starting, because the minute it starts to rain, all that oil comes to the surface and it doesn't wash away right away. And that's when cars have the tendency to hydroplane on the oil. Later on, they can hydroplane on water, they can, but it's more of a chance of hydroplaning on oil because oil is slicker. It's got a lower mu value, a lower coefficient of friction. Jack?
This might be completely wrong, but like when you play soccer on the asterisks or whatever, field, and you like step on it and it like swishes that part of the water, so long as it's trapped on there. Because like when you
No, I don't know.
because it like raises and when you push, you step on it, it pushes it down.
And then after you step off, does it come back?
Yeah.
Like a memory foam kind of thing?
yeah.
glide across the surface. Alright, so again, guys, to reiterate, two things. First, if mu is low, there is less friction. If mu is high, there is a lot of friction. To give you an idea, mu ranges traditionally between about 0.03 to numbers like 1.5. Teflon on Teflon is 0.04. There are things that are better than Teflon, but for the most part, that's the best example for you. So they'll range from these values all the way up to like 1.5. Okay? 1.5 would be like rubber on dry concrete. Rubber across dry concrete. That'd be pretty tough to move. Imagine, instead of, everybody knows, when you go on the airplane, you bring your wheelie bag or your carry-on bag, and you wheel it down the road, you walk into the subway. Imagine now if there weren't wheels, and the bottom of your carry-on was rubber, and you tried to drag it on the concrete. Wouldn't that be ridiculous? Wouldn't that be very difficult?
Yeah, at the airport, my wheels were in my
Wow.
And you had to do that.
Really tough.
I would just carry it personally, but yeah.
No,
That must have
You
been
just
hard.
you dragged it the whole way?
yeah, I was like 6 or 7, so.
Yeah.
First of all, confidence.
So rubber on concrete would be this end of the spectrum right here. Okay? Now, follow-up question for you. Follow up. A minute ago I gave the example of moving the desk. And to get the desk going initially is tougher than to keep it moving. To get the desk going initially, come on guys, listen, is tougher than to keep it moving. So it's harder for me to overcome the static friction than it is to overcome the kinetic friction. From that, can somebody make a statement about the relationship between mu s and mu k? Paul?
UK is less than or equal to US.
Very good. That's exactly right, Paul. Hold on. Since mu s is the static friction and it's tougher than kinetic, we say that mu k is either less than, I like how you said that by the way, less than or equal to mu s. Because certain materials, static and kinetic friction are actually identical. It depends on the materials, and you'll see that in your table. Teflon on Teflon, static or kinetic, it doesn't matter. They're both 0.04. But concrete on rubber is different. It might be like 1.5 for static and 1.4 for kinetic. All right? So again, the kinetic friction is traditionally less than that of the static friction. Questions on this so far? All right. We're doing well. Let's look at an example here. Let's do an example. A 24 kilogram crate, initially at rest on a horizontal floor, requires a 75 Newton horizontal push or force to set it in motion. So again, think about this table right here. For me to get the table in motion, it requires 75 newtons of force for me to push it. That's what's happening. Find the coefficient of static friction between the crate and the floor. Somebody tell me why it's static friction that we're looking for and not kinetic, Max.
Because it's the crate, isn't the crate originally at rest? So
Exactly. It's at rest. At rest means
It's not moving.
not moving. Good. Whenever something is at rest and it begins to move, the friction you're overcoming is static friction. Whenever it starts at rest, you're overcoming static. Now, once you get it moving, what are you then overcoming?
Then you're becoming static friction, and it's becoming kinetic friction or no?
What is it becoming?
Kinetic friction.
Kinetic friction. So, again, to reiterate for the 4th or 5th time here, once I get this desk moving, it's then kinetic. Right now it's static, but once I start moving it like this, now it's kinetic friction. But originally, this force I'm pushing with here is static, then kinetic. So, what do we say from last section that we always want to start these force problems with?
F equals ma.
That's our formula, and
Fine,
not time, no time here, no time is needed. A free body diagram. Please start first with the free body diagram. Take about 30 seconds. Try on your own to label the forces that are acting on this object. And don't forget about the vertical forces. There are So again, label all the forces that are acting on the object. Yeah, the force of push or pull. All right. Anybody want to come up and give me a suggestion? You keep writing. Want someone to come up and try and label the diagram what they think is right? So label all the forces acting on this. Give me your
Is this
sheet.
correct?
You're on the right track.
Okay, yeah.
You need other stuff.
Yeah. It's not possible. Why would you come to class without you're not prepared?
No, I came to class with 10 now it's garbage. I don't really know that. I don't know, I was writing down the problems.
You're right on the problem.
I was trying to write them down on YouTube.
I don't need the numbers, just the forces. Okay?
We don't have schools, right?
Right above it, right above it.
I mean, I can't write with this, so I don't know.
What is that? Okay.
So I don't know the substance. If you don't shoot it, isn't there like another
Jack thinks I could have found
norm? There's another normal force.
Good.
You know?
So, drawing
You
normal
guys
force acting
should
on.
see
I'm not quite done with you. Hey, does that say OP?
That's okay. What?
Okay.
Yeah, I'm not touching it.
Then there's one more.
Yep.
Then there's like. Then isn't there the friction?
Yep.
Isn't this acting like all along the bottom?
Let it start reading here. All right, Paul got all of them on here. Let's clarify what it should look like. Very good, Paul. So, first, the first thing that Paul drew was the force of gravity or the weight, but let's draw it from the middle. Okay, so I'm going to make a few corrections along the way, but his diagram is good. So we've got the weight of the object pulling it down to the earth. In response to that, we have the normal force acting up. So those two we had. Here's the force of gravity. This was Paul's normal force right here. Now, the object is being pushed to the right. So Paul put AP for applied force. Let's just call it FP for force of push or pull. Now, if the object wants to move to the right, which way is friction going to move? Or angle? To the left. So we draw friction like this. And I'm calling it FFS, the force of friction that is static. Again, FFS, the force of friction that is static. So that's our free body diagram.
Does it matter what side you draw it?
No. If you drew your pull on this side, then friction is that way. Now, keep in mind, the horizontal force is 75 newtons, which is positive. So I would have drawn it to the right for that reason.
No, I'm saying
It
like
won't
I did
affect your answer.
75 on this side, like pointing that way.
Oh, that's fine. Yeah, that's good. That's good. Look at it. We are trying to find the coefficient of little mu. So we need to find this and then break it down. All right. Equations.
Is that what you got?
Yeah.
Jeff, what's up? No acceleration. It's not moving. It's staying still. So, this object is sitting still. Did somebody fart or something?
I did not.
I
did not.
Go outside if you need to.
Go
on the object. So instead of saying sum of the forces equals ma, we can simply say sum of the forces equals 0. Again, the object is currently stationary. We want to get it moving. And we don't care about what happens once it starts moving, but we're trying to overcome its current static friction. In the x direction, I've got negative FFS. I've got the negative force of friction because it's acting to the left. I've got the positive force of push, so I put plus FP, and that equals 0. That's my equation in the x direction. In the y direction,
Is that a negative? Sorry.
there's a negative right there. Yep. In the y direction, it is not floating. It is not moving vertically. Therefore, there is no vertical acceleration. So again, we can say this. Guys, control yourselves. Come on. Stop. You can separate yourselves. You have to.
I did.
Now,
I've already separated myself.
good. Now, in the y direction, I've got gravity acting down. So we'll put negative FGY, or negative FG. Let's just put, sorry, negative FG. And then what's acting up again, everybody? The normal force, positive Fn. So there's my two equations right now. I've got two equations. What do I want? What was the goal of this problem to find? What are we trying to find? Jeff?
If 75N is enough, that's required.
Not enough, no. It said 75 is enough to move it. What are we actually trying to find?
You want the static friction between the crate and the floor?
Close, you're on the right track. You want the mu value, not the static friction. The static friction, Jeff, is right here, negative FFS. But, sorry, Jack, sorry. But we want the coefficient of static friction, which is mu s. So, please, write this as its formula. Again, force of friction is mu times Fn. So write this as mu static times Fn. Now, look at the x direction. I know Fp, but I don't know Fn. So I can't solve for mu. Does everybody agree with that? Again, look at your variables. You're missing two variables here. So you cannot solve for mu right now. But if you can get Fn over here, you can plug it in over here as a linking variable, like we did with time for projectiles. Again, solve for mu here you could, but we need Fn. So get Fn by itself. Add Fg over here. You get Fn is equal to the force of gravity. Real quick. Force of gravity is mg. You get a number from here. Plug it in for Fn. Fp was 35. Solve for mu static. This weekend, finish up problem set number 3. Your test is on Tuesday. On Monday, I'm going to try and review for about 20 minutes in the period. So come prepared with